So, hi everyone, this is Yuming. So I'm a thermal engineer from Meta, and I'm with Dennis from Microsoft. So today we will actually play a video first from one of our colleagues from Cool IT, and then we will start the presentation. All right, let's get started.
Hi, everyone. My name is Kiran Sumanchi, and I'm super excited to be here to present virtually on this exciting topic of air-assisted liquid cooling that most of the team has been working on for close to 2 years now. I'm going to kick things off with the why of AALC, and then I'll hand off to Dennis Chu, who's going to talk about the hands-on experience using AALC in lab environments, followed by Yuming, who will touch upon the spec, walk us through some of the builds of the photos, photos of the prototypes, and then end off with next steps for the committee. So without further ado, let's dive into the driving factors behind air-assisted liquid cooling, or AALC. We know that the component power and density is pushing the limits of air cooling. So AALC essentially is an enabling technology where facility water may not be available or may not be available as quickly as the technology demands for it. And thirdly, AALC is a low-cost solution to retrofitting an entire data center with facility water. And in addition, because water has a higher heat capacity than air, liquid cooling solutions are quite a bit more efficient for a similar power density and have the potential to reduce costs associated with operating the data center. So in essence, with this technology, we are extending the life of air-cooled facilities and adding optionality for DC owners. This is where we are today on the left-hand side, where forced air is used to cool a lot of the IT gear, and as component power and density increases towards the right, the AALC becomes that sort of intermediary step to direct liquid cooling. There's always going to be a place for air cooling, but AALC sort of acts as a transitional step to get data center owners more comfortable with the technology, especially with 100% liquid cooling. So there's two deployment approaches. There is, on the left-hand side, there's the door heat exchanger, and then on the right is the sidecar heat exchanger. So the door heat exchanger on the left, essentially the heat exchanger bolts to the back of the rack, and the RPU itself takes about 4U of space. And if you look at the top view here, you can see that the air flows through the IT gear before hitting the coolant in the heat exchanger at the back of the unit. Whereas with the sidecar deployment on the right, the cooling rack is adjacent to the rack with the IT gear. The RPU takes up 4U of space, but in the cooling rack rather than the IT gear rack. And additionally, the airflow does not pass through the IT gear before hitting the cooling loop. So there's some thermal efficiencies there as well. So let's go through the pros and cons of each solution. For the door heat exchanger, the biggest one is that it's compact and self-contained. Because there isn't a side car, that space can be used to put in more IT racks in the data center. There's also a common airflow for the IT and door heat exchanger, which makes it potentially easier to manage the thermal performance to a certain extent. The biggest con would be that the 4U of space is lost to the RPU, and because of the surface area, limits in the surface area of the cooling coils, a door heat exchanger will always have a lower cooling capacity than a sidecar version. And additionally, custom mounting brackets may be needed depending on the rack and rear door heat exchanger that you're using to hook the two up. For the sidecar heat exchanger, the pros are just higher cooling capacity because you have an entire tower dedicated to cooling of a larger surface area for coils, so that it makes it easier to achieve higher cooling capacities, and therefore allow for potentially chips with higher TDP per rack. Additionally, because there is no rear door, it's easier to deploy because you don't have to design any potentially design any custom mounting brackets, unlike the door heat exchanger option. And thirdly, the data center operators can squeeze in additional compute power within the IT rack because it's that 4U of space is not being taken up in the IT rack. It's in the sidecar itself. So once again, could squeeze in additional compute power within the IT rack itself. The biggest con is definitely how much space the sidecar takes up. That additional room could be used by another IT rack, so that could be a significant con depending on the data center operator and economics. So at this point, I'm going to hand over to Dennis Trieu, who's going to walk us through the operational learnings involved with the AALC solution. Thank you.
All right, thank you, Kieran. Within the last year, we've been testing out both solutions, and we've learned quite a bit about the both solutions. And I'm here today to present some challenges and learnings from both solutions. So let's start with the rear door heat exchanger. We have categorized into 4 main challenges for the rear door heat exchanger. The first category is system assembly. The rear door heat exchanger is the width of the rack and then the height of the rack, and it sticks about 1 foot out from the back of the rack. It weighs at least a few hundred pounds, so a single technician can't lift up and mount the rear door heat exchanger without mechanical aid. So to put on a rear door heat exchanger, they'll need some sort of lift or jig to lift it and put it on. The second challenge for our rear door heat exchanger is airflow characterization. In a rear door heat exchanger, the servers, the server fans, and the rear door heat exchanger and its associated fans are in series. The servers provide an impedance to airflow, and there are now 2 sets of fans in series, so they must work together in unison. If they don't work in unison properly, you can have air recirculation or not enough airflow or airflow bypass, reducing the amount of cooling. So some of the suggested ways to get around that is either have the server fans produce a certain amount of airflow or airflow pressure, or the alternative is to have the rear door heat exchanger fans communicate with the server fans so they can act in unison. One of the challenges in that is every single rack deployment in rack configuration at the L11 level would have to be tested to make sure that whatever servers are being put in with the rear door heat exchanger works properly together as a total system. In terms of the serviceability of the rear door heat exchanger, the rear door heat exchanger is serviced from the hot aisle. The hot aisle can be cramped and it can be quite hot, limiting the amount of service time in the hot aisle, and that poses a serviceability challenge for using the rear door heat exchanger. In the terms of server maintenance, it's a server maintenance from the back end from the server, the rear door heat exchanger has to be opened. And inside the hot aisle, when it's opened and running, it's going to start pulling air from the hot aisle, which is hotter temperature than the air coming out from the servers. So it's going to start reducing the cooling capacity of the rear door heat exchanger during these service intervals. On the learnings, we learned quite a bit about the rear door heat exchanger. We learned that once assembled together, the rear door heat exchanger can cool down 24 kilowatts in a complete IT rack solution in our prototypes. Through additional work in optimization and changing the boundary conditions of fluid coolant temperature and airflow rates, we can get that up to 40 kilowatts per IT rack. The rear door heat exchanger is an efficient use of space. It only sticks out 1 foot roughly at the back of the rack, and so it doesn't add too much to the floor space. When coupled with cold plates, it can enable higher density servers and higher TDP chips, and allowing us to run more higher power processors. And lastly, all the air, because it's in series, all the air that goes through the system makes it easier to cool down peripheral components that aren't being touched by cold plates, such as DIMMs, PCIe cards, M.2s, or E1.Ss. And since the whole airflow is going through and there isn't as much preheat anymore, these components, including power supplies, actually have a benefit to it. It's easier to cool them down, and we could actually have overcooling for those components. Moving on to the sidecar heat exchanger, we've noticed a few different challenges and learning opportunities. In terms of the system assembly, in this prototype, this unit was built in an ORV3 rack, and the ORV3 rack was modified to house this unit. In a manufacturing line and process, this would be not as optimal. We had to modify the existing chassis and place the components in and reinforce the structure, as well as there was a lot of components in the ORV3 rack that wasn't used anymore. So from a manufacturing point of view, making a sidecar heat exchanger that fits the same profile as an ORV3 rack for that space would be one way to optimize the manufacturing process, but yet still maintain our requirements. In terms of airflow characterization, because the sidecar heat exchanger is in parallel, in a data center, there's a limited amount of airflow per kilowatt, or airflow in general. So we're actually having airflow split between a sidecar heat exchanger and the IT rack. And a lot of these experiments that we were running, we would have 50 to 70% of the airflow going into the sidecar heat exchanger, and the remaining 30 to 50% going to the IT rack. This can be a lot less airflow than the IT rack is used to in the servers. So additional care must be taken to ensure that the peripheral components that aren't being cooled down by cold plates still receive enough cooling and enough airflow to properly cool them down. In terms of serviceability of the sidecar heat exchanger, since the sidecar heat exchanger is accessible from both the cold aisle and the hot aisle, it is much easier to service. And certain designs that we've seen, all the service can actually be done in the cold aisle if designed properly. And in terms of server maintenance, any server maintenance done on the IT rack doesn't necessarily affect the sidecar heat exchanger and any of the cooling performance, so that was a big plus. In terms of learnings, we've learned that the sidecar heat exchanger is easier to deploy than we thought. Taking a sidecar heat exchanger, we can rack and roll it. We can roll it into place, hook up the connections, and it's a lot easier on the commissioning aspect of things, not having to lift anything up too heavy. It doesn't require any IT rack changes and doesn't require any mounting points for that, and doesn't require us modifying the IT rack, with the exception of putting a coolant manifold. One of the interesting things we found out about the sidecar heat exchanger is that it can actually support more than one IT gear rack. It can actually be placed between two IT racks and service both the left rack and the right rack, provided that we put in the correct manifolding. Another addition to that is they can be chained together. Sidecar heat exchangers can be put together or beside each other for a group kind of environment, so increasing the availability for the cooling. So if one sidecar heat exchanger fails, it can fail over to another sidecar heat exchanger. And lastly, we experienced that we actually got better performance from the sidecar heat exchanger than we expected. We originally were testing out 24 kilowatts of cooling capacity for the IT rack, and we quickly found out that it can do up to 40 kilowatts of cooling capacity for the IT rack, and at different boundary conditions, flow rate, coolant temperatures, and airflow rates, it could be optimized to 70 to 80 kilowatts for complete cooling IT power. And for that, for rack space, that would also equal to 40 kilowatts per IT rack space. There are a lot of opportunities and advantages of using this air-assisted liquid cooling to extend air cooling a little bit longer in our data centers. And we have a few additional steps to help qualify this and push this along. In our work stream, we are planning to look at adding system integrators for our review for the testing and validation parts in this work stream. The other big challenge that I had mentioned is airflow characterization. In both the rear door heat exchanger and the sidecar heat exchanger, airflow management can be tricky in either within the racks or would require at the data center level or at the server level, in the case of the sidecar heat exchanger operating with less airflow. And through our learnings, we've learned that the potential of these, we can increase the potential to about 40 kilowatts of IT cooling in both the sidecar heat exchanger and the rear door heat exchanger, provided that we do some optimization, and that would be 40 kilowatts per IT rack space. So in a sidecar heat exchanger, that 80 kilowatts would be divided by 2 since it takes up 2 IT rack spaces. And I'll be passing this on to Yuming, who will be talking about the remote pumping unit specifications.
Thank you, Dennis. So Dennis already discussed like 2 different implementations of air-assisted liquid cooling solutions, and I wanted to actually dive deep a little bit towards to the RPU spec. So RPU, which is in short for reservoir and pumping unit, it is the brain and the hub of the entire AALC solution. So why we want to have this such spec? The most important thing is that we want to foster standardization and consistency so that we can provide requirements and also detailed implementations for the whole AALC solution. At the same time, we also wanted to foster the interoperability between the vendors. This is super important if we wanted to deploy at scale at the hyperscaler data centers. And hopefully with all those efforts, we can also increase wider adoption and also better ecosystem around the RPU. So moving to the next, I wanted to talk a little bit on the OCP specification outlines. So in total, in the specification, we will have 10 sections. So the first 3, scope, terminology, and overview, just set the context and the RPU relationship towards the other components within the AALC solution. And the next, we will actually discuss about the RPU requirements, which include both the physical dimension, the thermal performance target, the monitoring and interfaces, as well as the operational details. Following by that, we will have a detailed information with regards to sensor requirements. We'll have a really detailed sensor list that actually lay out the minimum requirement that we wanted to have the sensors within the RPU, and also for the whole AALC system. We will also discuss about the control schemes, whether the system is controlled by constant differential pressure or constant flow rate. At the same time, since alarms and field safety is really important, we also will discuss further with regards to how we deal with leakage and how the leakage between the IT rack versus the cooling rack actually interact with each other. Next, we will also discuss about like the environmental conditions for both operational and non-operational conditions. And also, more importantly, if we wanted to deploy the solution at scale, we definitely wanted to incorporate serviceability and operational impacts. Compliance and safety definitely as well. And furthermore, the spec also discuss about like the test requirements during manufacturing and also the long-term reliability that we require for this platform to be able to be in the fleet and operate efficiently and also reliably. So let's take a look at the spec itself, right? So this is a RPU which will be 4U height, and it is designed to fit into a 19-inch rack. However, with the adapter frame, we can also deploy this into an ORV2 or ORV3 rack, so that is quite flexible. At the same time, the RPU can take both DC power input directly from the bus bar or using the AC input. At the same time, for all the moving parts within the RPU, we have a requirement of N+1 redundancy. Specifically, it means for the pumps, we want to have like at least N+1 redundancy, as well as the fans in the RPU that cools the other components or electrical components and also the pumps. This N+1 redundancy also applies to true for like rear door heat exchanger or the sidecar heat exchanger. So we also wanted to have like redundancy of the hot swappable pumps, hot swappable fans on the heat exchanger itself. And as regards to the efficiency of the entire solution, we want the RPU together with the heat exchanger to consume less or equal than 5% of the entire IT power. And specifically for RPU, we hope it can be within 2%. At the same time, since the RPU is the control hub for the entire solution, so it is also responsible for controls and monitoring of the liquid to air heat exchanger. Last but not the least, we also wanted to provide like a standardization and also implementation details with how we actually do the standardized control and reporting interfaces to the upper management system, like building management system, or like rack management system, or even like the top of rack switch, well, Modbus or other type of interfaces. So with that, I wanted to also show some pictures of our prototype building. So we actually have, these are like two different implementations for the fixed pump version from both Cool IT and Delta. So we already got the sample and had gone through some of the initial testing and making sure the RPU is meeting the spec and meeting the performance target we are hoping them for. We also have like a hot swappable option within the RPU spec. This is mainly to, like, for example, if some of the pump cannot actually meet the lifetime expectations, then we definitely wanted to have like some easy to service model so that the pump can be easily serviced in the fleet. So Cool IT actually developed like one of the hot swappable version, and it can be like really easily to, while the system are still running, be very easily to actually replace one pump and replace the good pump in. So Dennis already provide like a very detailed implementations of like both RPU plus rear door heat exchanger and also the adjacent sidecar heat exchanger options. You can also probably find like a prototype at Meta booth, like in the expo hall. So for both of the solutions, like the RPU is kind of universal. So we always wanted to have like the RPU as a central control and monitoring hub for the entire solution. And also RPU is always placed on the bottom side of the two solution as well. So moving to the next, we wanted to actually have a signed final spec agreement for RPU and also go through the incubation community submission and also approval. And hopefully we can actually submit the spec to OCP early next year. So everyone actually can get access and build like the product from vendors, and also the hyperscalers can use them more easily. And at the same time, like this working community is also working very closely to develop a sidecar and also rear door heat exchanger specs. So that can be used like to foster entire ecosystem around this AALC solution. And with that, so if you have like more further interest into this topic, like we have a bunch of mailing lists you can actually contact with. That actually concludes our presentation today, and I wanted to open up the floor for any questions you might have.
So specifically regarding the requirements for the efficiency of the solutions, what temperatures did you take into account to calculate those percentages?
This is a great question. So with regards to coolant temperature, like we actually wanted to have the RPU spec up to like 40 to 45 degrees C. So that is actually kind of our requirement. We set up this 5% or 2% power goal for the solution and also the 2% for the RPU.
Okay, and for the air? For the air part of it?
30 to 35 C air, ambient air.
Okay. Thanks a lot.
What was the coolant flow rate you assumed?
So that really depends on the application. So for example, like if we wanted to deploy a solution that support like 24 kilowatt, and we are hoping that we can actually support like total 40 LPM for the RPU. And but that really depends on like what are the use cases and yeah, what are like the impedance level within the system itself. So.
Great, thanks for lots of great data. So the you talked about like up to 5% electrical power for the exchanger. That includes the fans and the pumps?
That is correct.
Okay, and have you done an analysis of how that improves the overall power consumption, like of the solution, or is that out of scope?
So currently, based on our testing so far, I think we are actually meeting the spec, and actually we are probably like around 2.5 to 3% for both the pumps and also the fans on the heat exchanger side, so which is actually pretty good.
Okay, great, thank you.
Were all the racks in your environment rear door cooled, or were there traditional style racks in the same space?
During the testing, we actually did this in a lab environment and not in a data center. So we just had a single rack by itself with the heat exchange solution. But there are additional studies to incorporate how this fits into the data center with traditional racks beside it.
Right. I was wondering, how did the hot aisle actually get hot downstream of the rear door cool? So it was a test environment. So.
Yeah.
You can do one last one.
Another one. Regarding the communication for this, how did you call it?
Air-assisted liquid cooling?
Yeah. So to characterize the air, did you you talked about communication between the servers and the unit as a system. Did you talk or did you think about electrical signals, or did you think about mechanical communication like pressure or something like that?
Those are both two different ways of doing it, and that we haven't decided on whether we're going to standardize on that or not. One thought is to have a communication cable from the RPU to the door and another signal from the servers electrically. And the other way, like you mentioned, is through pressure controls. So having the rear door heat exchanger actually have pressure sensors, either 1 or 3 or more, that measures the pressures from the servers and adjusts accordingly.
Okay. Thanks.
All right, great job. We thank our speakers.